In this video, we are going to walk through how to calculate a spring constant in physics. So let's go ahead and jump right into this example. It says, a vertical spring hangs from a ceiling. At rest, the spring has a length of 5 centimeters. When a mass of 10 kilograms is attached to the spring lengthens to 8 centimeters. Find the spring constant. Okay, so I've gone ahead and sketched out this situation. So we have this spring attached to the ceiling, and at rest, it has a length of 5 centimeters. So I've labeled this length as L sub I for the initial length of the spring. Now, when we attach a 10 kilogram mass to the end of it, it lengthens to 8 centimeters. So I've labeled this as L sub S for the stretched out length. So the stretched length is 8 centimeters. And our question is, given this information, what is the spring constant? So the spring constant is just a value that describes how stiff the spring is, or in other words, how difficult is it to actually stretch out this spring. So to solve this problem, here's what we can do. We can start by drawing a free body diagram. So for this mass right here, let's just draw a little dot to represent that mass. Now, what we need to recognize is that there are two forces that will be acting on this mass. The first is the force of gravity acting in the downward direction, so pulling it down. So we'll say the force of gravity. And that's simply equal to the mass of the object times the magnitude of gravity, so m times g. Now, there's another force that's acting in the opposite direction, and that's known as the restorative force, F sub r. And this is the force in the spring that is trying to restore this spring back to its natural length of 5 centimeters. So this is acting in the opposite direction of gravity. And this force, according to Hooke's law in physics, says that the magnitude of this force must be equal to k, the spring constant, times x, where x is the displacement of the spring from its natural length. So these are the two forces that are actually acting on this mass right here. Now, because we're talking about a vertical spring, here's what we can write. The net forces acting on this mass in the y direction are equal to these two forces added together. So this force, the restorative force, we're going to say that's in the positive direction since it's going up. So we'll say a positive k times x. But this force of gravity, this is in the negative direction. So we'll say this is a negative m times g. So we'll say minus m times g. And another thing that we know is that in this situation, this mass, when it's just hanging here and the spring has lengthened to 8 centimeters, it's just at rest. So these total net forces must be equal to 0. So what we can say is that this quantity must be equal to 0. And once we write this out like this, notice that we have everything that we need to solve for k, the spring constant. So here's what we can do. Let's move this mg to the right-hand side. So we'll say k times x is equal to positive m times g. And to solve for k, the spring constant, we just need to divide both sides by x. So here's what we get. That k, the spring constant, is equal to m times g divided by x. So let's go ahead and fill in the values that we know here. So we get k is equal to m, the mass, that's 10 kilograms, times g, the magnitude of gravity, that's just 9.8. So the displacement is simply going to be the stretched out length of the spring minus the initial length of the spring. So 8 centimeters minus 5 centimeters. Now, it's important to know that when we're calculating this spring constant, ultimately the units that we'll be using are newtons per meter. So we actually want to convert both of these centimeters into meters. So since there are 100 centimeters in a meter, all we have to do is divide both of these values by 100. So this 8 centimeters, when we divide that by 100, that's 0.08. So we'll say 0.08 minus, and instead of 5, we'll divide that 5 by 100. So that becomes 0.05. So we'll say minus 0.05. So this value is the total displacement of the spring in terms of meters. So if we simplify this a little bit, we get 10 times 9.8 is 98. 0.08 minus 0.05 is 0.03, and if you punch this into a calculator, it comes out to about 3,267. And as we mentioned earlier, the units for a spring constant are newtons per meter. So that is our final answer for this one. That is how we can calculate the spring constant given the initial length, the stretched out length, and the mass of the object that was actually attached to the spring.